Hello students, welcome back. In the previous videos, we went through the concept of kernel and image, the definitions of kernel, all the vectors in the original vector space V that are being sent to zero vector, that's a kernel, and the image, all the vectors from the target space W that actually came from the original vector space V. In other words, it's a set of all image vectors f of v's. So those were the definitions, and then we went through a couple of important theorems on images. 1.4 and 1.5. If V1 through Vn generate capital V, the original vector space, then their image sets, image vectors f of 1 to f of Vn generate the image space. On the other hand, 1.5 is backward. Instead of starting from the original vectors and then concluding with the image vectors, we start from the image vectors. If the image vectors f of v1 through f of vr form a linearly independent subset of the image space, then the original vectors v1 through vr form a linearly independent subset of the original vector space V. So it's backward. Here, original generate, then images generate. Here, images are linearly independent, then the originals are linearly independent. So generators and linear independence, those are complementary concepts, and then the directions are also reversed. So there's a duality going on. And how about the proof of the first theorem there? Well, we must prove that arbitrary selected element of the image vector space, that is, image vector, arbitrary image vector, can be written as a linear combination of f of v1 through f of vn. Whether this is true or not, that's something we have to prove. Now, what we know, v1 through vn generate the original vector space, so arbitrary vector from v can be written as a linear combination of v1 through vn. And then we'll use that. How do I do that? Arbitrary element f of v can be written as this v replaced by this linear combination from here, and then apply the property of the linear map, separate all the linear combinations, and then that's basically what we wanted to get from the beginning. Arbitrary element of the image space can be written as a linear combination of f of v1 through f of vn. We got it. Here we have these three lines, and then the first line is not really important. This is what we want to prove. It's a kind of strategy. It's not really necessary. This is what we are going to use, so it's necessary. And then this, of course, is the whole proof, the technical part. If you skip these two and then just answer just one line, yeah, I'll give you full credit, but it's not as good as having this one and also that one there. The first one, that's rather redundant. It makes the proof better, easier to understand, but it's not really necessary. Okay, let's go over to the second theorem here, theorem 1.5, but we'll approach in a kind of similar fashion. We must prove this. We must prove that these are linearly dependent. So x1 v1 plus dot 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 is equal to zero vector. Then all the coefficient must be zero. That's what we want to prove. By the way, wrong index. Have to go up to R. Okay, this is what we want to prove. Now, what we know that these are linearly dependent. we know these are linearly independent, so if I replace all these v's of f of v1 to f of vr, then all the coefficients has to be equal to 0. That one we know. And then let's prove. Okay, all right. This is what we want to prove, right? And then that equals to 0. So from here, let's apply the map F. Okay, all right. And then let's go to the next step. We can apply the property of the linear map. We can separate the linear combination. So it becomes this. And then what about the right-hand side? What is f of 0? It's always 0 vector, isn't it? Oops. Okay. So from here, we just use the properties of the linear map. We got that. And then we can apply this. Because that's equal to 0, as we have here. All the coefficient has to be 0. And by the way, that's something we wanted to prove all along, isn't it? And then this one actually came from here. So there goes the proof. This is what we want is to prove. We want to prove. And then this is what we need to use. We know that from the condition this the condition of this theorem gave us the following and this. Therefore, the following computation follows. If the linear combination is equal to 0, we can apply f. Okay, all right. Left-hand side and right-hand side is the same, so apply the same map. Okay, all right. And then you use the property of the linear map. We can separate the linear combination. And also, 0 vector always go to 0 vector. This is actually 0 vector in V, and this is 0 vector in W. And then you can use this, as I highlighted in green here. Consequently, all the coefficients are 0. So yes, that completes the proof. The first part here, this part is not really necessary, it's just for strategy. And as for this one, you can even skip this one too, because from here to there, you're using that. But still, I prefer to have this as a separate part. It makes the proof a little bit better. And this one too, it makes the proof a little bit better. A little bit redundant, I know, but it makes the proof better. But still, the main body is right over here. We don't have to talk about the second part, second statement, because we already discussed it in a previous theorem. And that completes these two theorems, 1.4 and 1.5, which kind of go in tandem, which complement each other. Next, let's talk about the theorem related to kernel. Let V and W be vector spaces, and let F from V to W be a linear map. Then F is 1 to 1 if and only if the kernel is just zero vector, nothing more. This theorem is about if and only if. So we have to prove both directions. Assume F is 1 to 1 and prove the kernel is just 0, and vice versa. Assume kernel is just 0 and prove that F is 1 to 1. We have to do both directions. Part 1 of the proof, and then we have to do part 2 of the proof. Okay, part 1, assume F is injective. F is a one-to-one function. That is, and then let's make a key observation here. What do you mean by that? That's the definition of one-to-one map, as a matter of fact. So let's analyze this. If the images are the same, then the original vectors must be same as well. You see, if the original are different, then there's no way we can have the same image and have one-to-one, you see. And this is, say for example, vector 2, 3, 1, and this vector is 1 to 1, yet they share the same image. That's not a one-to-one map. If we have the same image, then we have to start from the same vector. So that's the idea of one-to-one map. Are you comfortable with this? If you feel comfortable, then we can move on. Well, okay, I assume everybody feels comfortable with this. Same image means same starting, because if you start from two different vectors and then end up with the same image, that's not a one-to-one map. Okay, all right. And then we'll prove that kernel is just 0. All right? So let's select something from kernel. What do you mean by that? That means f of v is equal to what? What's the definition of the kernel? Set of all vectors that is sent to 0 vector. So select something from kernel means f of that vector is 0 vector. Okay, and let's make another observation here. Doesn't make sense. 0 vector always go to 0 vector. By the way, this 0 vector belongs to W because it's in the target. And this 0 vector, as a matter of fact, belongs to the original vector. It's the domain. Inside the parenthesis, so that's domain. But as a matter of fact, too many subscripts, just adding confusion. So this will be okay. 0 vectors goes to 0 vector. And what conclusion do we get? Do we get f is equal to 0? Oops. F is equal to 0. Yes. From here, you see, same image must have come from the same vector. That's what we are using here. V and 0 vector are two different vectors, yet share the same image. That's not a one-to-one map. So V is equal to 0. So what conclusion did it get? Element from kernel is always 0. Any element from kernel is just a 0 vector. So there goes the proof. So select arbitrary element from kernel. We prove that's 0. Let's prove the other direction. Let's assume kernel is just 0, and we have to prove 1-to-1. Okay, let's do that. That is, kernel is just 0. What does it mean by that? We belong to kernel. What do you mean by that? Wrong statement. These two are equivalent, right? V belong to kernel means f of v is the 0 vector. Let's go back to the definition of the kernel. It's a set of all vectors of v that is going to the 0 vector. So something belonging to kernel means f of that something is a 0 vector. So these two are equivalent. Okay, so what does that mean? F of v is equal to 0. That's equivalent to v belong to kernel. That means v is equal to 0. That's what this means. We can skip the middle part because that means the kernel. So assume kernel is 0. That means f of v is equal to 0 only when v is equal to 0. Okay. And then let's prove that the map is 1-to-1. If two function values or two images are the same, then what can you say about this? You can rewrite it like this. F of v1 is equal to f of v2. Flip 1 to the other side, and f of v1 minus f of v2 is equal to 0 vector. And then we can use the property of the linear map here. Then we can write it as f of v1 minus v2 is equal to 0 vector. Are you with me here? Okay, all right. And then please recall that kernel is 0, which means f of something is 0, then that's something. That vector has to be only 0 vector. So f of something is equal to 0, which means v1 minus v2 is a 0 vector. Okay, this 0 vector and that 0 vector belong to w, and this 0 vector belongs to v. So they may be a little bit different, but they don't really affect the conclusion. Conclusion is v1 and v2 are the same. Is that what we wanted to prove? Yes, indeed. By the way, let's do a bit of a color coding here. 1-to-1, and we use that at this step. And then kernel is 0, we use that at this step. And there goes the entire proof.